Welcome. This lecture is given annually by the recipient of the H. Bolton Seed Medal for outstanding contribution to teaching, research, or practice in geotechnical engineering. And before I get started, I want to just take a second, there it is, and recognize our previous seed winners. Okay, this year's H. Bolton Seed medal winner is Dr. Peter K. Robertson. Dr. Robertson may be best known for his work with the comb penetration testing and his soil behavior type classification system, which has become an industry standard worldwide, used by engineers every day. He is also recognized expert in liquefaction, and his CPT-based triggering evaluation methodology is also widely used. Dr. Robertson held the position of professor at the University of Alberta at Edmonton, where he taught courses, performed research, and led research teams, and held important administrative posts for 17 years. During that period, he instructed hundreds of students and supervised many master's and PhD candidates. He has authored 3 books, published 86 peer-reviewed papers in the geotechnical literature, and written over 100 additional papers and reports for conferences and symposiums. Sharing his expertise, experience, research findings, and insight is clearly one of the hallmarks of his career. He's received several prestigious awards, including 3 R.M. Quigley Awards, which are given by the Canadian Geotechnical Society for a Paper of the Year published in the Canadian Geotechnical Journal. Dr. Robertson has furthered the innovative work initiated by the late Professor Seed by advancing field tests for evaluation of liquefaction hazards. Professor Seed led the development of the SPT as a useful field test for liquefaction evaluation. Professor Robertson has led the development of the CPT as an equally or even more important field test for the liquefaction hazard evaluation. Both contributions led to major advancements in the state-of-the-art of geotechnical engineering practice. Dr. Robertson is truly one of the pioneers in the advancement of in situ testing and of our profession. So I'd like to ask Dr. Robertson to join me up here on the podium. Dr. Robertson, in recognition of your international reputation in the areas of geotechnical earthquake engineering, especially your use of in situ tests related to soil liquefaction potential, I present the 2015 H. Bolton Seed Medal.
Thank you, Alan. Thank you very much. Perfect. Here it is. Thank you. Perfect.
We look forward to your lecture, and thank you for your contribution and leadership to our profession.
Thank you. Well, thank you, Alan, for that kind introduction. And particularly thank you to the Institute for giving me this honor. It truly is a wonderful honor. And, you know, when I look at that list of names that I now join, it's an impressive list, and it's truly an honor for me to be even grouped amongst those individuals. I'd also like to thank the people that nominated me. You know, people nominate you for these things, and they write supporting letters, and I know some of them, and I really appreciate the effort they went to do that. But if I can have the slide, I'll try and get into the lecture and give you a little bit of background and some anecdotes about Professor Seed. I didn't really know him very well, but I did meet him a couple of times, and you'll see that reflected early on. And here it is. So why did I choose in the title that I wanted to talk about how far have we come in the last 30 years? Why did I choose 30 years? Well, I chose 30 years because 32 years ago, he was the external examiner on my PhD. One of the nice things about the graduate program in Canada is that every PhD student has to have an external examiner. And if you look carefully at the list of names there, Professor Campanella is the first signature at the bottom. He was my supervisor. But underneath that, you might be able to make out Peter Byrne's name and Liam Finn's name. And so Liam was the Seed medal winner last year. And so you can imagine, I had a pretty impressive committee that guided me. And then they asked Professor Seed if he would come up and be my external examiner. So he came up almost exactly 32 years ago to this week. It was in March of 32 years ago. So that was how I first met him, and hence I have his signature on my PhD document. So a little bit of a disclaimer. You know, it's a very large topic, and in the time, I can't really cover everything to the level I would love to. So I focused on in situ testing and really just the triggering element of seismic liquefaction. It's sort of one of the key elements. It's the one that's often most discussed, and it's fitting that I should discuss that, and it's one of the leading things that Professor Seed did. I'm going to exclude, you know, any discussion on the analysis, advanced modeling, and the elements of uncertainty. And I'm also not going to spend much time talking about static liquefaction, although I will touch on the definition of it and how it relates to seismic liquefaction, because it's very important that we understand the difference between the two. And clearly I'm selecting key milestones, which means I'm going to extend a little bit past 30 years. The 30 years was just the link to when I met him. And so I'm clearly going to miss some milestones due to time limits. And of course also, there's a certain selective bias. You may see some of the milestones with my name on it, obviously being a little bit biased, and a personal opinion. And of course, Professor Idris is here. And so I have to be cautious that at the end, I don't want him grilling me with questions just like Professor Seed did 32 years ago. So therefore, if I use up all my time, you'll know exactly why I did that. So, you know, like any source, you go to the true source of Wikipedia, which is what is the definition of soil liquefaction. Actually, it's not a bad definition. It sort of says it's a phenomenon that's most commonly observed in saturated, loose, sandy soils, and it's because loose sands have a tendency to compress or contract when sheared, whereas dense sands have a tendency to expand or dilate. That's actually not a bad, very nice generic. So soils have this unique characteristic in the sense of they tend to want to change volume when you shear them, and it's unique to the particulate nature of soils, and it's why we have problems. So what is soil liquefaction from a more technical sense? And so I'm going to reference CANLEX. Now, CANLEX is an acronym for the Canadian Liquefaction Experiment. It was a project I was involved in. It was a large collaborative project in the mid-90s, involved a number of universities, consultants, industry, and contractors. And the goal of it was we tried to go to 6 or 7 sites where we had picked out what we thought would be relatively uniform loose sands, and we wanted to characterize them as best we could. And it was 20 years ago. We did a pretty good job. And because it was collaborative, one of the first things we wanted to do was collectively agree on our terminology. So the terminology we chose was cyclic liquefaction, but more commonly people often refer to it as seismic liquefaction because it's often associated with earthquakes. And that's where loose sands can reach the condition of zero effective stress under cyclic loading. But we also identified static liquefaction, or sometimes referred to as flow liquefaction. We actually preferred the term flow liquefaction because it's not always triggered statically. Sometimes it is triggered seismically, and so it can be a little misleading if you just use the term static. And that's really the process of strain softening of a soil. So I'm going to talk mostly about seismic or cyclic liquefaction. I'll use those terms interchangeably. And of course, the lab evidence of that is fairly well understood. On the left, you've got the classic sort of stress path diagram, and on the right, the stress strain diagram. And so what we've observed is that when the cyclic stress is larger than the static stress, so you can get shear stress reversal, then if you have shear stress reversal and you build up pore pressure, it is possible to reach the condition of zero effective stress. And so as the pore pressures build and the effective stresses decrease, the soil softens, the stress strain curve becomes softer, and then eventually when you get to zero effective stress, the soil essentially achieves zero stiffness, which means you can have large deformations. It doesn't have zero strength, it has zero stiffness, and that results in large deformations. So loose sands can reach it fairly easily. Dense sands have a tendency to dilate, so dense sands tend not to get all the way to zero effective stress. They can build up pore pressure, but they don't always truly get to zero effective stress, but they do soften and they can deform. And clays, of course, can soften. If you hit them with a large enough cyclic stress, they will deform and they can develop positive pore pressures, but they don't reach zero effective stress, so they don't lose all of their stiffness, so they tend not to liquefy, but they do soften. And so there is the term cyclic softening that tries to capture the response of clay-like soils to cyclic loading. So over the years, there's been lots of major earthquakes with significant liquefaction. So what are the common things we've observed from those case histories? And a lot of it, when we look at the soil, they're predominantly young Holocene age soils. They're predominantly non-plastic or low plastic sandy soils. They're generally uncemented. They're predominantly silica-based sandy soils, essentially almost no carbonate-based sands. There's little or no stress history. They're typically young, essentially normally consolidated. K-naught's often nominally around a half. And the database from the case histories, they're mostly for the larger earthquakes. We have a tendency to bias towards sites that liquefied. In other words, when liquefaction occurs, we go to those sites and we study them. We tend not to go to sites that didn't liquefy. And so our database, 70% of the data in our database tends to be liquefied sites. And so we really are underutilizing the massive case histories of non-liquefied sites. And they tend to be shallow. All of the case histories are essentially less than 12 meters. And that's because liquefaction is based on observed surface observations. And they're mostly essentially level or gently sloping ground. You see the pictures underneath from the history of the earthquakes over time. Now, static or flow liquefaction, that's where the soil can strain soften. And so that's why it can be triggered statically. So if you have a soil that can strain soften, like a very sensitive clay, then the sensitive clays of eastern Canada experience flow liquefaction slides. We tend not to call them flow liquefaction slides, but they are. They're where the material has strained, softened, lost a considerable amount of its strength that results in large deformations. Now, it can be triggered static or cyclically. And the key is the static driving stresses have to be larger than the resulting minimum or liquefied undrained strength. In the clay world, they tend to use residual strength. In the sand world, we're now tending to use the term like liquefied undrained shear strength. And you have to have a kinematic mechanism. You have to have a geometry where instability can result in deformations. Now, if there's only a little bit of material that strains softens, it may in fact be contained deformation. That material may in fact strain soften, but there's enough strain hardening material that the deformation is somewhat limited. Or if there's a lot of the strain softening material, the mechanism becomes uncontained and then results in large flows. Oops, sorry. And so case histories, the one I've shown here, a very famous one, Stava Tailings Dam, that was in 1985. It's always a good one to show because 268 people died from this event, and the geotechnical engineers went to jail. And so it's a good example to show because particularly for young engineers, it illustrates maybe the significance of some of the decisions we make. And then the one below is the Tennessee Valley coal tailings failure in Kingston in 2008. So common features again, very young deposits, non-plastic typically or low plastic materials, uncemented again, predominantly silica-based soils, little or no stress history, and they're very loose. They're highly contractive materials. And common instability features, sometimes the triggering is very minor disturbance. I was involved in the Jamuna Bridge failures, which were multiple submarine slides during the construction related to the bridge, and the disturbances were really very minor disturbances that triggered these instabilities. You don't need big earthquakes. Failures tend to occur without warning, so they occur very rapidly, and so the observational approach tends not to apply because you don't have time to respond to it once it triggers. So they're potentially very dangerous events. So as part of the Canalex project, we did develop this flow chart, and sometimes a lot of people forget how useful this flow chart is, and so I wanted to show it again. The only modification I made is at the top, when you characterize the soil. Originally, I used the term strain softening and strain hardening, which is generically the correct way to do it, but I've sort of modified it and sort of throwing in the generic terms of contractive or dilatant. And here I'm referring to contractant or dilatant at large strains, and you'll see why I chose that terminology later. And so if you've got a contractant material, strain softening, then you could trigger flow liquefaction, but you've got to trigger it, and you've got to have the gravitational shear stresses larger than the resulting minimum undrained strength. And then, of course, it could be contained or uncontained. If it's uncontained, they're often progressive failures, and they often move rather rapidly. Now, the material could be either contractive or dilatant at large strains, but if you hit it with a big earthquake, and big earthquakes essentially result in shear stress reversal almost everywhere, and so then you can get cyclic liquefaction. So even materials that are dilatant at large strains can in fact experience cyclic liquefaction if you hit it with a large enough earthquake. And that can result in very large deformations. But if you look at the flow chart carefully, it also has another element to it that's nice, because underneath cyclic liquefaction, you'll see there's a little arrow that comes around and says possible pore water redistribution that can come around and then make a material that initially was dilative and actually turn it into a material that's now contractive. You know, as the pore water redistributes, it flows into an area that it can make the material looser, and because it's now looser, it may in fact become contractant and therefore may become strain softening. And in fact, after the cyclic liquefaction, you could in fact trigger flow liquefaction subsequent to the event. And those that went to the meeting this morning about liquefaction, about Christchurch, they made the observation that, you know, at shallow depth they were observing that there was a time delay for the buildup of pore pressure because of the consolidation of the sediments below that had liquefied, water flowing upwards, flowing into an area, and therefore the pore pressures continuing to increase with time after the earthquake. So the maximum pore pressure actually occurring about 5 minutes after the earthquake at shallow deposits, and then in some cases the lateral spreads and deformations being observed after the earthquake because of that pore water redistribution. Now, as practicing engineers, this is problematic for us because it means that I could go out and do an investigation, determine whether or not I think the material is contractive or dilatant, and yet after a major event, the material's behavior could in fact change. And that's worrying for us. How do you cope with that? And of course, one of the guiding principles would be, well, recognize that pore water redistribution could occur and stop it occurring. You know, put drainage in so that the water doesn't redistribute into areas you don't want it to. So I'm going to focus now just on seismic or cyclic liquefaction. And you know, the sequence that most people use to evaluate it is primarily for level or gently sloping ground. Is there's sort of three elements to it. One is the material susceptible to cyclic liquefaction? And then, is the event large enough to trigger it? And then, if it's triggered, what sort of deformations may result? And certainly in the last 30 years, most of the focus has been on the triggering, and that's why I'm going to discuss it now. And of course, we just don't have enough time to cover it widely, so I will focus primarily on that triggering element. So a little bit of historical context, and you know, quite often when we talk about the history of evaluating soil liquefaction, it all often comes back to that 64 events of the Nagata earthquake and the large earthquake in Anchorage, Alaska. Those two big events really triggering the whole development, and Professor Seed really was one of the innovators, and Professor Idris was one of his students, and so the two of them were just heavily involved in all of those early developments. And one of the key first steps was this so-called simplified method, which you know, I was corrected that really the origins of it was the simplification to calculate the demand from the earthquake, this cyclic stress ratio, how to calculate that and to come up with a very simplified way to do it, which was truly a big breakthrough because earthquake loading is very complicated, it cycles and etc. So you've got magnitude and acceleration. How do you cope with all of this? And they really sort of simplified it down and said, hey, we could come up with this simple way of calculating the load from the earthquake so that we have some mechanism of starting to study the problem. And so in the early 70s, they sort of developed the early concepts of how to calculate the cyclic stress ratio from a simplified approach, and then they used primarily relative density to sort of guide them using case histories. And then it was in the early 80s, there's actually a number of references. I checked with Professor Idris, and he suggested the 92 nomograph for EPRI was probably the best one to go to, about 82. And that's where they really started to introduce the concept of, well, getting relative density is very difficult, getting samples, so maybe we should go to in situ testing, and at the time, the standard penetration test. So they sort of introduced the concept, let's use the blow count, but we are going to have to normalize it for overburden. That led to N1, and then we needed to account for the variation of the energy of the hammer, so we needed N160. So they came up with the broad concept of correcting the blow count, and then, of course, noticing that you would get different blow counts in siltier sands, and so they came up with this idea of of this clean sand equivalent. I don't think they actually used that term then, but it's a well-accepted term now of the clean sand equivalent penetration resistance, which was the measured one with some correction. And they recognized that because they were doing the SPT, they had a sample, so they could send the sample to the lab, get the fines content, and so they could turn this test from one measurement into maybe two by using the fines content as an index of the soil, of the siltiness of it, and the correction was based on the fines content. So that was really a big leap forward. And then you notice along the top I'm adding in some of the major earthquake events. So clearly as time's progressing, more earthquakes are occurring, and so the knowledge base of case histories is growing, so the number of dots on the charts tends to grow. And so in NSEER, the workshops were 96, 97, and then they produced the report essentially in 2001, sort of a consensus report, which really didn't change things very much. The curve just kinked in a little bit at the bottom, but basically it didn't change. More data points were added. And then since then there's been updates, and Professor Idris updated in 2008, and then recently 2014 they I don't think they really adjusted the SPT one very much. Well, they changed the fines correction. So there's been ongoing updates. So you look at that one slide there and you start to realize, wow, Professor Idris was involved in 71 and he's still involved today, 40 years later. That's an incredible achievement to have played a significant role for over 40 years. So the origins of the method was very clever, where they had this simplified approach to estimate the cyclic stress ratio from the earthquake, and then with the penetration resistance, they came up with a way to normalize it for overburden pressure, and then a way to correct it to clean sand equivalent. But there are a number of assumptions that they had to make. They've got this stress depth reduction factor, RD, the magnitude scaling factor. There's also a K sigma for higher overburdens when you're designing outside of the database. And CN itself plus the fines correction. And so you see now that the plots have a lot more data on it, a lot more dots. But most of the data is concentrated in a relatively small area. Most of it's in that main area. We don't have a lot of data outside. So the curve has to be extrapolated beyond there. And there are a number of competing curves, but in fact they don't vary that much where most of the data is, because after all they're fitting the same data. Now the fines content correction. The observation was silty sands essentially have a smaller penetration resistance for the same resistance. Now that's an important observation to frame it that way. It's not that silty sands are more resistant, it's that they have a smaller penetration resistance measured in the field for the same resistance. And so this clean sand equivalent was basically a correction to use just the single clean sand curve and correct everything over to that clean sand curve. And the early days it was an additive correction, and the fines content is used as an index of soil behavior. Okay. Now, one of the difficulties with fines content, it is a physical characteristic. You're going to throw the soil into a sieve analysis, and you're going to measure the amount of material retained on the 200 sieve. So it has a relatively weak link to the in situ behavior, because it is a physical characteristic that's weakly linked to behavior. Now there is a link, but it's somewhat weak, and it's a little bit difficult to measure and apply in variable soils, as this photograph from Professor Bollinger illustrates. Real soil is often very variable, and so how do you make sure that the fines content you have represents that material? And then also we're missing some other important features, such as mineralogy of the fines, of which plasticity index can also be used as an index of that mineralogy. So, one of my first controversial slides, and I put the blame on Professor Main. He wrote a nice state-of-the-art paper for the International Society. In there he quotes that engineers have a full sense of reality in their ability to assess each and every soil parameter from a single n value. Soil is very complex, and yet we try to capture it with a single measurement that's clearly not very feasible. Or at least in today's world, it's not feasible to do that. And so I add the point at the bottom, and I think Paul would agree with me, is that geotechnical engineers in the 21st century should progressively stop using this crude, unreliable test. Now, Paul and I have been saying that for 20 years, and I don't see it changing very much as we creep further into the 21st century, but I'm forever hopeful. So, of course, I want to talk about the CPT. So what are the advantages of the cone? Well, it's fast and continuous. And when I say fast, that means 2 centimeters a second, so it's about 3 feet a minute. So you can do a 50-foot sounding in and out in less than an hour. Very repeatable, so 2 different contractors essentially get the same answer if you do them right next to each other. Economic and productive. Strong theoretical basis. There's been an enormous amount of progress on the theory of analyzing the CPT because it's essentially a quasi-static test. It's not having to cope with the complex dynamics of the dynamic test. Measures more than one parameter. So, most cones now, they measure tip, friction, and pore pressure. So three parameters continuously while you push this thing in the ground. They're essentially 3 independent parameters. And of course, nowadays we've got additional sensors. So we can measure shear wave velocity and P wave velocity as well. And I'll talk about that, as well as other things too. There's actually a multitude of sensors that can be added. You can have a soil moisture module that measures dielectric, so you can actually estimate the water content in fine-grained soils, plus a number of other things. Now, the limitations, somewhat high capital cost, although the cost is constantly coming down. The electronics is cheaper, and you can actually get into CPT relatively inexpensively nowadays. Somewhat skilled operators, they have to know how to operate basic laptop computer. You don't get a soil sample, and that's often held up as the biggest criticism. And that's often why people will say, well, that's why we do the SPT, because, yeah, we think the CPT is good, but you don't get a sample, so I'll do the SPT because I get a sample. And of course, that's hogwash. You don't get a sample while you're pushing the CPT, but you can push samplers with the CPT equipment, and I'll illustrate that. And of course, the other limitation is limitations in gravel. And that's, again, somewhat overrated because you can push the CPT into all the same gravelly soils as you can do an SPT. Give you an example. I'm an advisor to Greg Drilling. We did a project just recently in the Santa Ana River, and it was in gravelly soils. And they had the Becker rig out. The Becker tested down to about 50, 60 feet. The CPT came out, and they thought, well, you'll get down 20 or 30 feet. We'd like to see the data. We pushed 150 feet in gravels. So, of course, then the owner had to call up the Becker rig and say, you guys better get out here again because they just pushed cones 150 feet through this gravel and you stopped at 50. Get back out here and drive that Becker a bit deeper. So you can do CPTs in gravelly soils more so than you think you can based on growing experience, as long as you've got good push force. If you've got the ability to push with about 20 tons, you can push into pretty stiff material. In fact, if you can push with 20 tons, you can push into any material that has a blow count up to about 100. Now keep in mind, SPT blow counts become highly unreliable past 50 because the relationship between resistance and blow count becomes highly nonlinear in a dynamic test like that. It's essentially a miniature pile driving, whereas the CPT, of course, continues to stay linear. So you can push into very hard material, and in Southern California, we constantly do that with our 25-ton rigs. And you don't need specialty cone trucks to push 25 tons. You can do that off the back of a drill rig if you just anchor it down. And the Christchurch experience is showing that if you require them to do CPT like they did in Christchurch, they went from one small contractor that had a little bit of CPT equipment to about 15 contractors now operating in Christchurch, poking 18,000 holes around the city, varying from small, lightweight equipment on bobcats to large 25-ton trucks. But in terms of soil sampling, there are, the Dutch have been doing CPT for 50 years, and they've got a variety of samplers. The most common is this sort of sampler that here is used in North America quite a bit. It looks just like a cone. It's just got no electronics in. It's about the same size as a cone. It's about 1 inch in diameter sample. And so what you do is you push the cone, you get the soil stratigraphy, you identify the layers that are of most importance to you that you'd like to verify the soil type. And so you move over a short distance, 2 or 3 feet, and then you go down with this sampler. But you're not restricted to pushing at 2 centimeters a second. You can go as fast as the hydraulics can. And on a lot of these trucks, the hydraulics will go 20 times faster. So you can zip down and get this sample really fast. And so you can get 3, 4 samples in 20 minutes. and bring them back up to the surface and then show them to the engineer, cap them and send them back and do grain size and Atterberg limits to classify the soil. So this is a typical example of what you see. Here's an example cone profile. So you've got tip, friction, then you've got this thing called friction ratio, which is the ratio of the sleeve to the tip, and then pore pressure, and then the soil behavior type, and it's color-coded. The yellows and browns are essentially the sands, and the greens and blues are the fine-grained soils. And this example, there's a number of soil samples to illustrate. Yes, you can get soil samples too, and it's pretty quick. And the ideal thing, instead of taking samples every 5 feet, which is what you would traditionally do in drilling, you get samples in the layers that are of most interest to you. So based on the stratigraphy that you have and the project requirements that you're facing, you choose to take the samples in the most appropriate layers. So rather than come back with 100 samples, of which none of them are in the most critical layers, you come back with a small number of samples, of which every one of them is in the layers that are most important to you. So a little historical overview of the CPT. Again, a little selective. I chose the Robertson and Campanella paper after my thesis, but in fact, Seed and Idris did have a paper a little bit before there where they also included elements of CPT. So Professor Idris reminds me that he has been promoting the use of CPT from the early 80s. But in those early days, we had very limited case history data. So in the early days, we actually converted the SPT over to an equivalent CPT so that we could begin to develop experience, and the Japanese were getting a little bit. So a little anecdote about Professor Seed when he grilled me 32 years ago. So that little diagram on the right, it was a diagram like that in my thesis. And he said, I notice you're not extending the line down to 0. He said the SPT curve goes all the way down to 0, but you're stopping it and it doesn't go to 0. Why is that? And I said, well, in the SPT world, it's possible to get a 0 blow count. If you're in very loose material, the weight of the rods can exceed the strength of the soil and you'll get 0 blow count, which is an infinite inaccuracy of the measurement. Whereas with the CPT, you never measure 0, because even if you were to lower the cone in water, you will measure the hydrostatic pressure of the water. So you'll never measure 0 with the cone. And in fact, in clean sands, you basically never get a normalized cone resistance of less than about 20 on average. It's very rare to see anything that low. And so therefore, the curves stop there because basically you can't expect to see anything below there. And so the anecdote was he asked me that question 3 times during my defense. So he asked it first time, and I gave him that answer, and then he asked it 2 more times spread over the next hour or so, as I think he was really making sure he understood exactly what I said. And by the 3rd time, yeah, he nodded and said, yeah, I got that. And so the early ones, of course, it was tip resistance and fines content. And then in '98, I had a student, Catherine Ride, and then we put together the paper where we made the leap forward and said, well, I'm not sure I like this fines content. Can we just use the cone data and this soil behavior type index, which I'll describe in a second? And so we came up with a simple correction. And it was a multiple correction, not an additive correction. And that's a slightly controversial issue. And I argue that the multiple one is actually easier and more correct because the relationships rotate, they don't shift. And so the fines content correction that's additive becomes rather complex because you've got to keep changing the additive for different penetration values. So you have these rather complex relationships because you've got to keep changing the additive. Whereas if it was a multiple, it's a single multiple that just changes with the soil behavior type. So it becomes a lot simpler. And then in the NCR workshop, a slide update, they sort of went with it. Notice how I'm also showing as the cone is evolving that you're getting towards the seismic CPT that's measuring more parameters, but the triggering curve is not fully making use of that yet, and I'll touch on that later. And then, of course, in recent years after the NCR, there's been a number of papers. Moss et al. Out of Berkeley, they did an update that included probability. So there was enough now case histories to have enough that you could actually start to do some probability on it. And then Idris and Bollinger and Idris sort of did their update in 2008 and 2014, where more data points are added, so getting even better. And they added probability as well because, again, enough data points where you could adequately do that. My only criticism a little bit is I think a slight retrograde step of going back to the fines content. And in fact, for a lot of small to medium-sized projects, people don't measure the fines content, because to get enough of it to develop the relationship is quite difficult and it's expensive. They just don't have the budgets to do it. So people actually stick with IC, but you then introduce the uncertainty where you convert IC to an apparent fines content and then put the apparent fines content into the relationship. And I think it's an unnecessarily extra step. And why do I think that? Because okay, the soil behavior type chart's been around, as you heard in the introduction, and the normalized version, this new normalized chart has only been around 25 years, and it's beginning to catch on. I say that to graduate students. If you develop something that you think is great, yeah, it could take a few years before it catches on. So this new one has been around 25 years, and the nice thing about it is that the CPT is responding to the in-situ behavior of the ground in terms of strength, stiffness, and compressibility. That's not exactly the same as our traditional classification systems. Our traditional classification systems are based on physical characteristics, which is essentially Atterberg and grain size limits. So you get a disturbed sample, and then you run Atterbergs on the fine grain, and you run grain size on the coarse grain, and you're running them on disturbed samples. So it's only a relatively loose link to its actual in-situ behavior, whereas the CPT is in fact responding to the in-situ behavior. And it's loosely linked to this physical classification system. So one of the problems with the chart in a way is that I chose to use the traditional, what are often referred to as geologic descriptors, such as sand, silts, and clays, even though they are really derived from our physical classification system, and they're not strictly the same as the behavioral one. But of course, that's what industry is used to, and so that's what's put on the chart. But I still get emails from people around the world saying, hey, I'm using your chart, but you got it wrong. You said it was a silty sand, but it's actually a stiff clay. And it says, yeah, okay, stiff clays will plot high up on the chart. And so, but from a behavioral characteristics, they're beginning to behave more like these stiff, silty sands, even though it's a clay. So it's the behavioral, it is in fact capturing the correct behavior, just that we struggle a bit sometimes to put the correct words in it. So this was, I think, the real turning point when Mike Jeffries and Mike Davies, both in Vancouver at the time, they put this idea together that said, look, when we look at these normalized soil behavior type charts, the boundaries on this log-log scale, they look roughly like concentric circles. So they came up with this brilliant idea that said, hey, we could join these two normalized parameters to come up with a single parameter that they called the soil behavior type index. Now, I had to modify it slightly because they had suggested it for their chart when their chart was a little bit different. It was using the normalized cone resistance that had pore pressure, which can be problematic at times. And so I preferred to stick with the basic one. So I had to modify it slightly. And it was only a very small modification. And so sometimes people think there's actually two soil behavior type indexes. There's the original Jeffries and Davis one, and then there's the Robertson and Ride slightly modified one. But they're not much different. They only differ a little bit when you get down into the clays. And it's primarily a function of soil compressibility. So as the soils become more compressible, then IC tends to get bigger. And note that although it's using both parameters, it is predominantly dominated by the normalized cone resistance. It's less influenced by the friction ratio. So in terms of determining the susceptibility to liquefaction, there are a number of methods. In the old days, it was the Chinese criteria, which is pretty well debunked now, and much more moving to plasticity index as a sort of a physical characteristic index of the soil. And so Citadel had theirs, and then Bray and Sancho had a sort of similar one. They're all sort of built around the concept that when the PI, the plasticity index, starts to increase, you start to move to a more clay-like material, and then they become less susceptible to liquefaction. But it is a transition, and in fact, Professor Idris and Bollinger, they nicely use that term clay-like and sand-like, and they discussed that there was a transition. They had suggested a PI normally of around 7, whereas these two are both suggesting around 12. And on the right, I show the CPT soil behavior type, and I'm arguing, saying this is a behavioral characteristic, not a physical characteristic. So they're not strictly the same, but it works out that An IC of about 2.6 historically is often associated with PIs of around 10, so there is about the same boundary. And maybe one of the mistakes I made is in the early days I said, I think 2.6 is a reasonable cutoff. Now, I did say in the fine print, it's roughly 2.6 plus or minus a little bit. But of course, everyone said, oh no, Peter says it's 2.6, and suddenly 2.6 was written in stone, and it had to be 2.6. And it says, no, it's plus or minus. And it depends a bit on the mineralogy of the soil, etc. So there is a transition zone. And so when we look at the case histories, this is from Bollinger-Idris update, so more case histories. And you see that they all tend to plot in the sand and silty sand region. And in fact, nearly all of the case histories do plot with IC less than 2.6. And when you go to the trigger curve, there's now quite a range of curves to draw from. And again, I don't show it with the dots on. And in fact, I can't really fairly show it with the dots on because every method is making different assumptions on this RD, the magnitude scaling factor, and how they normalize and what the fines content correction is. So in fact, I cannot show the dots because although they're using essentially the same case history, the dots move around based on the assumptions they've made. So it is in fact a package deal. So if you're going to go with one of the methods, you've got to go with the package deal. You've got to calculate cyclic stress ratio the way they tell you to do it, and you use their cyclic resistance ratio curves the way they tell you to do it, and it's a package deal. But again, where most of the data tends to fit, the curves are not that much different. Now, it looks like the Idris and Bollinger one is a little bit lower, slightly higher, and that's partly because of the different assumptions in the fines correction and magnitude scaling factors, etc. So they shift a little bit. So the clean sand equivalent, how did I get that clean sand equivalent? Because in fact, when you go into most of the publications, most of them don't tell you how they get the fines correction. They just say, here it is. And they say, well, we use the case histories, and so we use the case histories to get the fines content correction, but it's a little complicated on how they did it. How I actually did it is I plotted the data on the normalized soil behavior type, and I could draw the boundary for a given roughly cyclic stress ratio or cyclic resistance ratio. And you draw a curve, and that results in the correction factor. And so what comes out of that was this observation that you could have two different soils that would have two different cone values or penetration resistances, but yet they have essentially the same resistance to cyclic loading, and hence the clean sand equivalent value that would capture that. So why do I like that approach is because it's a behavioral characteristics that has a strong link to the in situ behavior. And it's developed from the case histories similar to the way the fines content one was, but it doesn't use fines content. So is there a theoretical basis for this correction? Now, there's a lot of theoretical work done, and of course, I could spend my whole hour just talking about the work that people have done on the theory, but I want to just talk very briefly about critical state soil mechanics approach and state parameter, really sort of spearheaded by Jeffries and Bean, who've really devoted the last 30 years of their life to this. And they quite often show the plot that critical state soil mechanics is built around the concept that if you shear a soil, it will have a tendency to move towards its critical state. So whether or not you shear it drained or undrained, it'll eventually move towards its critical state. And that critical state as a boundary can be represented as a line in terms of void ratio against log of mean normal stress. And they represent it as a straight line. And Professor Bollinger quite nicely combined that concept with all of Bolton's work on curvature of strength envelope of sandy soils and came up with a generic sort of critical state line that is highly curved at very high confining pressures, which is important to recognize. And Bean and Jeffries recognize that. They just argue and say, well, over the stress range of most problems, you can simplify it down to a straight line. But it is important to remember it is curved, it's highly curved at high stresses, which influences a lot of things which we don't have time to go into. But if I want to summarize Bean and Jeffries' work of 30 years, then they showed that it depends on in situ stresses, K0, mean normal stress, the shear stiffness, the shear strength, compressibility, and plastic hardening. And it requires a combination of in situ tests, ideally seismic CPT, which I'll talk about, and lab testing to get the critical state line, supported by extensive calibration, both calibration chamber work, and then Canlex came along with its ground freezing to get undisturbed samples, which was also a key part of the database. And in the end, they came up with sort of two approaches. One was a simple screening method where you could estimate state parameter, and then another one where on high-risk projects, you could do the full Monty. You could go out, you could do seismic CPT, maybe even self-boring pressure meter to get K0, get samples, disturb samples, do reconstituted testing to get critical state, do numerical modeling and link it to interpretation of the CPT. Whew, it's pretty heavy going. And there's a few projects that have used it. Come on. But the screening method, now first suggested by Pluis in '92, and I updated it in 2009 onto my soil behavior type chart. But essentially you get a family of contours of state parameter. And those contours are essentially contours of dilation angle. So how much a soil is likely to dilate at large strains. And you see the arrow will show that as you move up in the chart, soils become more dilatant. And Bean and Jeffrey sort of suggested that a state parameter, not of 0, but nominally of about minus 0.05, would be that boundary between soils that would be dilative at large strains or contractive at large strains. And it applied primarily to young, uncemented silica-based sands. Important caveat. So if I put the state parameter approach next to the curves that came out of the case histories for seismic liquefaction that produce curves of what are essentially clean sand equivalent curves, when you put the two together, you suddenly see, wow, they look a lot alike. So the one on the left, which is sort of the critical state framework approach on state parameter, very complex, but you end up getting this family of curves. And when you look at the ones on the right, based 100% on case histories from seismic liquefaction, they're essentially very similar sets of curves. So it sort of adds some weight that there is a theoretical basis of why we make this correction to a clean sand equivalent, why silty sands, they give lower penetration resistance, but you can correct it up to an equivalent clean sand as a basis of doing things. And in fact, it shows that on that boundary of that minus 0.05 between dilative and contractive soils, it's about a clean sand equivalent of about 70. And so there is a simple little relationship of how you can estimate state parameter from the clean sand equivalent. And in fact, when you go to the case histories of flow liquefaction, and a number of these were statically triggered, when you look at the ones that had modern electric cone data and you plot those on there, sure enough, they all plot on the contractive side of that boundary. Even some of the sensitive clays plot correctly on the contractive side. And the reason there are big ovals there is that's all of the cone data in the layer that was considered to have triggered instability and suffered strain softening, and the dot in the middle is just the mean value. So it's encompassing all of the data. It's a little bit conservative by encompassing all of the data. But because of the risk of consequence of flow liquefaction, yeah, you need to be a little bit conservative. And this was a slide, in a way, I borrowed from Professor Idris. It's not exactly the slide he had, but it's the concept that if I show that boundary line between contractive and dilative on the case histories for seismic liquefaction, you do in fact see that a large percentage of the case histories of seismic liquefaction are in fact on the dilative side. So dilative soils can experience cyclic liquefaction. In other words, at small strains, they will develop positive pore pressures, and so they'll soften, and then it's only at larger strains where they begin to dilate up. So a large percentage of the case histories are in fact on moderately dilative materials, and it's a function of how big the earthquake is. If the earthquake is big enough, you can trigger it to soften. And here's an example of the state parameter approach. This is from a publication from Bean, from 75 meters of tailings beach sand deposit. So that's a very deep profile. And the far right plot is from the very detailed numerical modeling that they carried out, and the one next to it is the simple screening approach. Now, I know it's hard to read the scales, but essentially they're giving very similar answers. And so a number of these projects now, these case histories where people have done extensive work, showing that there is, in fact, very good agreement between the simple screening method and the detailed modeling, as long as the materials are young, uncemented, and essentially silica sand based. And of course, a lot of tailings fall into that category, and that's often where it's applied. So I'm proposing that we move to sort of a modified soil behavior type, and I've been promoting this for a couple of years. This is where I think the future is going, is these normalized soil behavior type charts, is maybe we should move away from these traditional geologic descriptors like sand and clay, and maybe move to terms more like it's a coarse-grained dilative material that's predominantly drained, or it's a coarse-grained contractive material that's predominantly drained, or it's a fine-grained dilative material that's predominantly undrained, or it's a fine-grained contractive material that's predominantly undrained, and there's a transition zone in the middle. And the curve is essentially represented by that clean sand equivalent of 70 in the coarse grain material, and then it curves over to essentially an OCR of about 4 in the fine grain material. And those are the boundaries between the two. And I think that's where the future is going to go, where we actually use behavioral descriptions to capture the behavior of the ground. Now, I'd probably take another 20 years before we catch on, but I think we're going to get there one day, or something like that. So I'll touch briefly on seismic. I'm going to speed it up a little bit. And so the advantage is that it's economic and productive, strong theoretical background. You know that the small strain shear modulus is just the shear wave velocity squared times the mass density. It's a fundamental parameter, the small strain stiffness. It can be measured in all soils. This is another great thing, whether or not it's really, really soft clay through to a rock. You can measure shear wave velocity. And in gravels. Another nice feature, you can measure it both in the lab and in the field. So it's a way of linking the two. So if you get samples, you can measure shear wave velocity in the lab and check that you're getting roughly the same answer as you're getting in the field, so that you're comfortable that the samples are undisturbed and that you've got the right stresses on it. Now, I'm just illustrating downhole seismic as an example. There are, of course, many different ways to measure shear wave velocity, each having their own advantage and limitation. I'm just illustrating that one. Now, the limitations, often you need somewhat skilled operators. That's a little bit sophisticated to do it. You don't get a soil sample if you're just measuring shear wave velocity. And, of course, it's occurring at very small strains, which people tend to freak out about. And it's a somewhat insensitive parameter. You know, all of the liquefaction case histories tend to fall between 100 and 230 meters per second in terms of normalized shear wave velocity, which is a relatively narrow band, which means if you're going to use it, you need to measure it accurately. So you need to measure this number pretty accurately if you're going to truly use it in a meaningful way. And I think we're going to see huge developments in the coming years in how we measure it increasingly more accurate. So the historical context of the use of shear wave velocity, there's been a number of publications. Okay, slightly biased, I'll show mine as one of the first ones. But I think Andrus and Stokey really was the first that started looking at a significant number of case histories and showed that there was essentially no correction for fines. That was one of the nice things. Shear wave velocity is essentially independent of the fines because it's such a small strain measurement, whereas penetration resistance is such a large strain measurement. So it becomes somewhat insensitive to that fines, which is a very nice feature. And then Kayan, more recently, et al., of course, they increased the size of the database to over 400 cases. They traveled all over the world, really did an incredible job collecting this data, and you see an example of their plot on the left there, the number of data points. And because there was a large database, they've added probabilistic to it, so they've tried to actually put some probability as opposed to just a single trigger curve. So huge advancements. Now, the nice thing about if you go out and measure seismic, so P waves and S waves. So S wave, the shear wave velocity is independent of saturation and groundwater. It's controlled by effective stresses and density and age and cementation, as I'll get to later. And the P wave velocity is controlled primarily by saturation. So if the soil is saturated, you essentially get 1,500 meters per second. And if it's slightly unsaturated, you get a big drop in P wave velocity. So P wave velocity is really a very nice measure of, is the material saturated? And I think we're going to see a growing use of that. And I'll give you an example. Professor Jamlikowski, in a number of his lectures in recent years, has shown this example from this large tailings dam in Poland, where they did extensive site characterization, including measuring P and S waves, and they were clearly able to show the saturation line in the tailings. And certainly for this structure, it was important to show that where the dams were, the saturation line was dipping significantly down, so drainage was very effective, and therefore they felt that the risk of static liquefaction was significantly reduced because of that. So I think we're going to see increased use of that measurement. And so I borrowed this slide from Paul, or at least the nice graphics part of it. And so Paul and I are big fans of the seismic CPT. I added the little element in there, developed since 1983. So, you know, a lot of people say, wow, this is a new test. And you say, that's been around for 30 years. It's not that new a test. And in fact, a lot of contractors have been doing it for 30 years, so they have a wealth of experiences and data. So when I joined Greg in Southern California, I suddenly had access to a wealth of data. You know, all of their cones are seismic cones, so They do seismic CPT on relatively large percentage of their projects, as do other contractors like Conetech. So there's a growing experience of measuring this and how to measure it, how to improve the accuracy of it. And so 7 measurements. So you've got tip resistance, sleeve resistance, pore pressure, shear wave velocity, and of course you can measure P wave velocity if you want to. And then if you stop and let the excess pore pressures dissipate in fine-grained soils, you can get the time it takes to dissipate about 50%, like the T50 value, as a measure of the rate of dissipation. And you can get the equilibrium pore pressure to actually determine what the piezometric profile is. So you can get 7 measurements in one cost-effective test. Let that sink in for a second. So that one blow count is why I think you should stop doing the SPT and why you should start to do tests like this. This is 7 parameters in a highly cost-effective way in essentially a continuous manner. Not every 5 feet, but every couple of inches. A lot more data. Now, one of the great things about CPT is continuous data. One of the disadvantages is it's continuous data. And you have to cope with that in your analysis. And there are some tricks that you have to make sure you cope with. And so here's the other slide I borrowed from Paul, is that traditionally shear wave velocity with seismic CPT, you measure it every meter. And the origins of that is the push rods are a meter long, and so you're going to stop every meter and add another rod. And so that's a convenient spot to measure shear wave velocity or P wave velocity if you want to. And so traditionally it was always every meter. But you can do it continuously, and Paul's developed this very nice little automatic hammer, and you can have it programmed to hit every 1 or 2 seconds. I think in this example it was every 2 seconds. And so here is a compilation of all the waves, and it's basically wave traces every 10 centimeters in essentially a continuous mode. And so I think the future is going to be is where the seismic CPT will in fact become continuous. So you don't have to stop and hit the beam to get the shear wave. You have this thing going automatically in the background, either as a vibrator or one of these simple little hammers, and you can collect continuous shear wave velocity with a pretty high accuracy and get a nice detailed profile. Now, something we don't talk about very much, and I looked at it in my thesis and it's still worth mentioning, is in 1980, Professor Marchetti in Italy developed this flat plate dilatometer. Now, we don't use it a lot here in North America, but it's a clever little test. So it's a flat plate, and it's got this little membrane on it, and so you push it in just like you would push a cone in, but you stop every 8 inches or so, or a foot if you like, and you stop and you inflate the membrane and you measure the pressure to just inflate it, which is like essentially the in situ stress around the blade, and then you inflate the membrane 1 millimeter and you get the second reading, and those 2 readings you can use to calculate normalized parameters, which he then developed a series of empirical correlations. So it's a very nice test, relatively inexpensive. It is a lot slower than the CPT, so here in North America that slowness means increased cost, and so it is about 3 or 4 times slower, but it produces some quite nice data. And one of the nice things, it's more sensitive to horizontal stress than the cone is. The cone is influenced, the cone tip resistance is influenced primarily by the mean normal stress. So if K0 doubles, the cone tip resistance will go up about 60%. It won't double. Whereas with the DMT, it's 100% influenced by the horizontal stress. So if K0 doubles, the dilatometer value doubles. Just like the shear wave velocity will double. If you double K0, shear wave velocity doubles as well. It's directly proportional. And so here's a quick overview of the history. The real downside is that because we don't use the DMT very much, we have very few case histories. So recently, Marchetti and I have been in discussions about really the conversion from CPT to DMT, a bit like we did 30 years ago with the SPT and CPT, is can we take this large database from the CPT and convert it over to get some better basis of how the DMT might work. And that's what we do now. And I'll show an idea at the end about where it's going. So other developments that we really didn't have time to talk about but are worth mentioning, the increased use of probability to define the trigger because of the growing number of case histories, the increased use of forward modeling to evaluate the methods when new case histories. So Christchurch is a good example. So Christchurch had this series of earthquakes, quite a few of them, 4 big ones and some smaller ones, where they had liquefaction occur or didn't occur. And now they've got 18,000 CPTs. And so now you can take these methods and take the full digital profile and run it through the methodology as you would do if you were designing. So forward modeling, say, hey, let's assume I don't know anything about this site. I go and push a few cone holes. What would I have predicted compared to what observed? And not just the triggering, but the consequences. So how much deformation occur? Am I getting close to predicting a reasonable consequence of the earthquake loading? And so we're seeing an increased use of the full digital profile, not just the single value. And a greater emphasis on the post-earthquake consequence, how much settlement and lateral spreading occurred. So what are some of the new developments? And I of course, only have time to touch on a few, but a few that I think you might find interesting. And so the current trigger methods work well when the soils are young, uncemented, essentially normally consolidated silica-based soils. You notice I kept repeating that because it's an important thing to keep in mind. And of course also if the depth is relatively shallow and the earthquakes are within a given range. So what do we do when soils and sites don't exactly match those features? How do we cope with that? Now I can't go in all of them, but I want to just really talk about one that I think is quite useful. Is again, these case histories are mostly soils that have relatively little or no microstructure. They're young, uncemented soils, essentially normally consolidated, so they don't have much microstructure. And so soils that have microstructure have somewhat unusual characteristics. So I sometimes just say they're unusual soils as an easy way of saying they have soils that have unusual characteristics because of microstructure. That's a bit of a mouthful. Some people just use the term non-textbook soils. So what is microstructure? Well, the big factors are often things like aging, cementation or bonding, weathering, cold welding if the material sits there for a long time, which is similar to aging, and of course stress and strain history to some degree. And how do we identify that? Well, it's a combination of things. One, of course, is background geology. So is the geology telling you it's older or likely to be cemented? The mineralogy, is it carbonate where there's a high risk it could be lightly cemented? And of course, sampling and lab testing. But I'm just going to talk a little bit about the in situ testing, and I've identified seismic CPT and seismic DMT. So what's the schematic behavior of ideal and structured soils? So on the left, a sort of Serge Louet suggested this simplified description and saying, sort of the ideal soil is a soil that is essentially somewhat elastic and then it hits yield and it's plastic. It's very, very straightforward, has a very well-defined limit state or yield curve. Whereas soils that have some microstructure, they're the type of soils that tend to be elastic and stiffer longer. So they will stay elastic longer until they reach their yield, and then the effective microstructure begins to break down, and then they come back to the more ideal. So they tend to be stiffer at small strains, but they tend to have similar behavior at large strains. And so the nice thing about something like seismic CPT is the shear wave velocity is a small strain measure. It's controlled by things like the state of the soil, either relative density or OCR, effective stresses, age and cementation. And the cone resistance is controlled by all the same things, but it tends to be less sensitive to age and cementation. So there's a strong relationship between the cone resistance and shear wave velocity, but it does depend on microstructure. You have to account for age and cementation. So you can link the two. Come on. There we go. And so about 20 years ago, I had a student that came up with this very nice idea of plotting G over QT against the normalized cone resistance. So normal, and this is in sandy soils, so the normalized cone resistance is essentially like relative density. It's the state of the sand. So for clean sands, it's like that clean sand equivalent, so it's directly linked to how dilative the material is. So the bigger the normalized cone resistance is, the denser it is, the lower the normalized cone resistance, the looser it is. And then G over QT, that's essentially like a rigidity index. So in a lot of our theoretical work, we use rigidity index a lot, particularly in behavior clays, things like cavity expansion to model cone penetration resistance. Rigidity index pops up a lot, and rigidity index is the stiffness to strength, G over SU in clays. So it's this stiffness to strength ratio, and that's what G over QT is. It's the small strain stiffness to the strength, where the cone resistance is an index of the strength. So it's like a form of rigidity index, a very powerful concept. And so, but 20 years ago, we noticed that most young uncemented materials fell within a very narrow band, and then soils that had some microstructure tended to fall outside that band. And then Schneid noticed the same thing. He added more data in 2005. And then James Schneider and Rob Moss had a small little paper in Geotechnique quite recently where they added a lot more data. And they came up with this parameter kg that they called, that I'm actually saying, well, it's like a normalized rigidity index. So it's rigidity index, but it's been normalized by the state of the soil. It's a very powerful concept. So it's a normalized rigidity index, and they found that for young uncemented sandy soils, it typically was less than about 300. And then once that number got higher than 300, you were into soils that were aged or cemented or had significant microstructure. And this is what they showed. Here's the equation. So it's that G over QT. So G0 is you're getting from shear wave velocity. QT, of course, you're getting from the cone. Hence, the seismic CPT is attractive. Gives you both of them. And then you've got this normalized cone resistance as a measure of the state, and you calculate this value. And they said basically when it was greater than about 330, it was likely to have some significant influence of microstructure, and if it was less than that, it was likely young and uncemented. And in fact, for most of the liquefaction case histories, the average value is about 200. And they showed a lot of data to support that. And so here's this idea of this normalized rigidity index. And I've extended it a little bit further. I've actually extended it up into the fine grain region. And it shows this range for young uncemented soils, roughly between 100 and 300, with the average of 200. And then anything larger than that, and you've got some microstructure. So here's the more generic form. Coarse grain soils tend to be to the right. Fine grain soils tend to be the left. And there's a transition between the two. And in fact, I've even added the little arrow of PI in fine grain, that when you've got the different mineralogies of fine grain material, that's how that rigidity index changes. And that's well established from lab data, but if you put it into this form, that's what it looks like. It's a very powerful concept. And in fact, when you're screening through data, this is actually a very good screening mechanism to thin out the unusual materials that are fitting outside that bound. So it's a good way to identify these unusual materials. And so Andrus actually had an idea like this. So Ron Andrus, he did that early work with Stokey, and then he's at Clemson University. And he suggested this idea of this somewhat awkward number. It's like this measure to estimate shear wave velocity ratio. Whew. So it's the measured shear wave velocity divided by the estimated shear wave velocity, typically estimating it from the CPT. And he showed that, the cyclic resistance ratio for the aged deposit would be the one you would have estimated for a young deposit with some correction, and the correction based on either age or this MEVR number as a measure of age. And Ron also, he didn't really say it in the paper, but essentially he was saying it, there's also a difference between geologic age and behavior age. So you might have a Pleistocene deposit that actually has a Holocene behavior age because it's liquefied at some time in the past, and so its behavioral age is much younger than its geologic age. So the shear wave velocity is telling you its behavioral age. And in fact, and so Ron then went further and said, hey, you could actually get these family of triggering curves where the triggering curve would be larger for the older deposits. So he actually suggested that, that as these older deposits, you would not use the traditional triggering curve that came out of these young, uncemented materials. You would increase it because of the beneficial effect of aging, and that shear wave velocity was how you would do this. So it's essentially saying, hey, you could use the normalized cone triggering curve, but yet boost it up for aging effects, and you get the aging effect from shear wave velocity. The weakness a little bit is you have to estimate the shear wave velocity, and so you have to have a correlation, and there's some uncertainty in that correlation, so it introduces a slight element of uncertainty there. But if you take this normalized rigidity index approach that Schneider and Moss had suggested, that gets around it because the estimated value of this kg is actually about 200. That's what they showed. Because it's a normalized value, you don't actually have to estimate it. It says, yeah, no, for case histories, it says that estimated value is 200. So you go out, you measure shear wave velocity, you measure the cone resistance, you calculate this normalized rigidity index kg. And of course, if it's larger than 200, there could be some microstructure and it's beneficial, and you can account for that beneficial effect. So that's where I think the future is going to go, of how to identify soils that might have unusual characteristics. Now, I live in Southern California, and of course, we have big earthquakes, and we have a lot of young, uncemented soils, and so not that big an issue, although we do have older sediments, and we do have some cemented sediments. But when these methods are transferred around the world, and you need to extrapolate, or if you come to the East Coast where you may have older deposits and smaller earthquakes, then issues like this can become very important, that you're dealing with older deposits, and if you use the traditional simplified approach with these simplified trigger relationships that are all based on young uncemented materials, you're going to be highly conservative. And so these methods are a way of avoiding that excessive conservatism by using shear wave velocity to help you. But one of the questions comes, and I asked Rob Kenyon this question about a year ago. I said, now, I've got access to a lot of seismic CPT data, so I've run quite a bit of analysis of looking at liquefaction based on cone data and looking at liquefaction based on shear wave velocity. And if it's young uncemented materials, essentially they give very similar answers because they should do. They're all based on similar case histories, etc. But if they give different answers, which one's right? So, for example, if the cone says it's going to liquefy, but the shear wave velocity says it's not going to liquefy, which one's right? Now, based on Andrus' work, it would say, well, if it's primarily from aging, the shear wave velocity is probably right. And that's the one you should go with. But the issue comes is that if you have a soil that's lightly cemented, and so the increase in shear wave velocity is due to a small amount of cementation, the question then comes is, well, if the earthquake is quite big, and the earthquake could exceed the threshold strain, which means that it will actually start to plastically deform this cemented material, you could break down the cementation and it goes back to being an uncemented material, which would then mean the cone would get it right. So for small earthquake, the shear wave velocity gets it right, but for large earthquakes, the cone gets it right. So the need to be able to tell the difference, and in fact Schneider and Moss had suggested that threshold strain was one way that you could make a decision on that boundary between the two. So clearly more research is needed. We need more knowledge about what the threshold strain is. And in fact, the talk this morning out of Christchurch, they were showing that when they use T-Rex to generate shear strains and generate pore pressures, they're able to calculate what the threshold strain is. And they were typically coming up with values that are very close to the values we would traditionally assume, which is essentially about 0.02 to 0.04% shear strain, or 2 times 10 to the minus 4 for shear strain. So to sort of finish off, where some of the future too is combined tests. Now I was talking about the seismic CPT, but Marchetti is quite keen on the DMT, and so he's now suggesting that there's a similar effect where because the dilatometer is more sensitive to microstructure than the cone is that KD is not always the same as the cone resistance, this KD parameter that you get out from the dilatometer. It's essentially the normalized liftoff pressure, which is why it's called K, and the D for dilatometer. And so he's saying that for low values of KD, you essentially have young, normally consolidated, uncemented materials. But if KD is high, then you can come in with your cone resistance, and then you can sort of boost the sort of cyclic resistance ratio because of this higher KD that's warning you about this unusual characteristic that could be beneficial. So, I've tried to summarize, historical development of triggering, and, we talked a lot about the simplified method, but I want to just finish off by talking about the importance of geotechnical risk and what that means, and what level of sophistication is required for a project, and that's controlled by the risk of the project. And so, there's sort of the definition of geotechnical risk, and this came out of other work that I can never quite remember. I think it's Haidt and Louet, essentially, but David Haidt had suggested this criteria. It's essentially what are the hazards, and we're often talking about earthquakes, and of course it also involves the geologic complexities, and then the probability of occurrence, what's the probability the earthquake's going to occur, or increasingly, what's the probability that the design earthquake is going to occur simultaneously with the maximum groundwater level that you're assuming too, which we often overlook. And then, of course, what are the consequences? And then also, I like to add, what's the experience of the engineer? What's the local experience? Because if there's a lot of local experience, that helps mitigate the risk somewhat. Sorry, it skipped a slide, sorry. So what's the appropriate level of sophistication, both for the site investigation and the analysis? And David Haidt had suggested this criteria, which I really like. It says there's 4 basic criteria. It says, so what's the level of local experience? How complex are the design objectives? What's the level of geotechnical risk, which is essentially controlled by the consequences? And then what's the potential for cost savings? And often that last one is often a dominant one. What's the potential you're going to save money here? So if the local experience is very good, the design objectives are relatively simple, there's a relatively low geotechnical risk and relatively low potential for cost savings, then we often traditionally in geotechnical engineering use traditional, often simplified methods. So in fact, the simplified approach is often totally appropriate for low-risk projects. But for high-risk projects where there's often poor local experience or complex objectives, high risk in geotechnical terms, as well as the potential for significant cost savings, then often we need to do a lot more complex material. So although I've talked about things like CPT and seismic CPT, and I've talked about simplified triggering methods, etc., clearly this is just the screening. So for high-risk projects, that would be your initial screening. Do I have a problem? If the shear wave velocity and the cone data plus other things are saying, look, you don't have a problem, then chances are you don't have a problem. If, however, they say there's a potential risk here, then you need to go on and do a lot more sophisticated stuff. And in some of the big tailings projects, now they are doing this full-blown critical state analysis and trying to do much more sophisticated interpretation of the data. And then, of course, and then doing numerical modeling, and then using that sophisticated interpretation of state parameter and critical state to feed into the numerical modeling that they subsequently do. So, in summary, I'm wearing you out, and I'm also running down Professor Idris's time for questions, because I've also noticed he's been frantically taking notes, which is now worrying me. So, in summary then, simplified method still tends to dominate practice. I mean, I didn't talk about some of the other methods, but it still dominates practice. And that's because it's pretty good. Every time we have a major earthquake event, it shows that, yeah, it did a pretty good job at predicting what was going to happen. A growing number of case histories, 250 for CPT, and that shear wave velocity one was over 400. But we're still getting liquefaction failures, and it's not because of the weakness of the method, it's just that there are many sites that have not been evaluated, and of course then they get hit by a big earthquake and they have problems that they didn't really expect, and Christchurch in a way was an example there. The triggering relationships in many respects haven't changed very much over the years. They've been relatively stable. So in a way, it's time to stop adding more dots to the curve. I think now the focus is much more of doing the forward modeling and looking at the consequence. These triggering relationships are in fact fairly stable, and it's now looking more at the consequence. That's where the future is going to be. You're going to see increased use of CPT, hopefully decreased use of the SPT, increased use of that soil behavior type, and we are seeing it. Christchurch is using it as a primary index of a lot of what they do. Growing awareness of the importance of both shear wave velocity and P wave velocity, particularly P wave velocity, in terms of determining is the material saturated, and if it's not, or even using methods that may reduce the degree of saturation as a way of mitigating the liquefaction risk, and using P wave velocity to confirm it. Growing use of seismic CPT because of many independent measurements. We need a lot more research on these soils that have microstructure and how they affect how we do things. Growing use of risk and probability, although I do find that when you talk to companies in small to medium-sized businesses doing everyday geotechnical, they struggle in terms of how to use probability in communicating both internally and externally to their clients. When you go to a client and say, hey, I used a factor of safety of 1.3 or whatever the number is, and the client sort of understands that and says, oh, okay, I got like a 30% buffer in there. That sounds good. Now, if you say, well, there's a 10% probability it's going to fail, they don't like that, even though they may be the same thing, but there's a whole educational element on probability that I think is one of the reasons why the whole application of probability has struggled a little bit to become accepted in practice, partly because everyday engineers struggle to actually understand what it means, and then they struggle of how they're going to communicate it. So I think that there's a big need to improve that. It is going to come, there's no doubt about it, particularly on high-risk projects where you have educated clients, but it's going to have a transition period. And I think we're going to see a growing use of numerical modeling, particularly on high-risk projects. But there's a real need to link the in-situ data to the parameters. I still see people where they say, well, we ran a FLAC analysis or we ran a Plaxis analysis, and we did this sophisticated numerical analysis. And you say, well, what data did you base it on? Well, we got a couple of blow counts. It says, well, hold on. You went out and did a couple of SPT blow counts, and then you did this complex numerical analysis based on a handful of blow counts. That's not a good way to go about this. if you're going to run a complex numerical analysis, you need good quality data that's got a consistent framework about how you are going to estimate those parameters. And a lot of the work that people like Bean and Jeffries have done sets an example of how that could be done. So, I covered a lot of ground there, and I really want to acknowledge a lot of my colleagues and my mentors, really. My time at UBC, Professor Campanella, Finn, Byrne, and Vade, they were tremendous colleagues and mentors for me. And then when I went to University of Alberta, Professor Morgenstern and Seago, tremendous colleagues and mentors. And I spent a year and a half in Italy with Professor Yamlakowski, and tremendous time for our family. And of course, like any academic, tons of great graduate students. And most academics, they acknowledge that some of their graduate students are really bright people. They're a lot brighter than we are. And without them, you can't do a lot of this work. And of course, in recent years, the support of Greg Drilling, I have a dream job. I work for a contractor, and he pays me very well. And I won't say how well. Might disappoint my academic colleagues. And I have a corporate credit card, so I don't have to complain to my granting agency about traveling. They don't question too much the credit card bill. So, dream job. And of course, I couldn't do it without family, and my lovely wife Linda is here. And Kelly, I get to work with my daughter. She also works with me, and so I'm privileged to have a supporting and loving family. So thank you. I'm sorry I took so much time, but I wore out Professor Idris's question time.